In this example, the data from the settling test are provided along with the initial suspended solids concentration. You are asked to determine the detention time and overflow rate that will result in 60% removal of suspended solids. The data from the settling test are shown here. For example, after 10 minutes, a sample was collected at a depth of 0.5 meters. The suspended solids concentration in this sample was determined to be 14 milligrams per liter. A sample was also collected at a depth of 2.5 meters. The suspended solids concentration was determined to be 17 milligrams per liter.
So what we need to do is we need to take this data and put it in a form that allows us to do the analysis. I'm going to switch out of PowerPoint into Word, and I've got the Word document posted on LonCappa, so you can follow along with that Word document. So what we need to do next, as I mentioned, is to convert the suspended solids concentration to % removal. And not sure who's mentioned before about the solution, but thank you. So we have a suspended solids concentration of 20 milligrams per liter. And for instance, if we take this or a set of data, it's straightforward. We have 20 minus 14 over 20, and that's equal to 6 over 20, which is 30%. So what we need to do, and what I've done here, is I've just taken the data from above, and in Excel, I've calculated the % removals. So that part's really straightforward. The next part is the challenging part. What we need to do is plot the iso concentration lines. So what we're doing is, notice here, we have time here, and we've got time here. So what we're doing is we're just taking that data, so that time data, and we're just now putting it in rows. We have in the table here the % removals. So if you look here initially, what we have here is at a depth of 2 meters and 10 minutes, we have 20% removal. So here's your 20% removal. So for 20%, in order to achieve that 20% removal, we need to wait 10 minutes or take that sample at 10 minutes at 2 meter depth. We'll do the same thing for 30, and this was the 30% right in here. And you see at 0.5, 10, so at 0.5, we have 30%. At 10 minutes, 0.5 depth, we have 30% removal. If we look at, this is 50%, and I apologize for writing over the line, but this is 50% here. That corresponds to 20 minutes at 0.5 depth. So this one here corresponds, and the red lines, the red are kind of the easy ones to deal with because they correspond to the % removals that we're looking at for iso concentration lines. So if you look, let's look at this one here. We have 40%. So that 40% occurred at 35 minutes, so right here, and a 1.5 depth, so that corresponds to this one. I'm just going to put a little asterisk next to it, just to. And we continue in this way. So like I said, the cells in red are the easy ones to deal with. And then what you need to do is you need to interpolate. And in some cases, you'll be interpolating, for instance, between vertical values. In other cases, you're interpolating between horizontal values. And that it's not trivial. It takes some time. But we do this interpolation. And by doing the interpolation, what the goal is to get these ISO concentration lines. So we've plotted data here, and then this is here, the ISO concentration line corresponding to 40%. So we do this for each of the percentage lines. So for instance, here is our 78% line. So this is 70%. This makes sense so far? We then, in order to determine the removal, what we're going to do, and we'll look at here, we start with 70 minutes. So, and we have to make an assumption. So let's assume that we're designing a sedimentation basin clarifier with a depth of 2.5 meters. So if we're looking at that, we're at this depth right here. And let's start by looking at we'll assume that we've got 70 minutes. We have to make some assumptions to start with. So if we have a detention time of 70 minutes, then we have an overflow rate of 2.5 meters divided by 70 meters. Let's convert this to minutes per day. And that gives us an overflow rate of 51.4 meters per day. Or you'll often see this written as meters cubed per meter squared per day. So that meter squared is the surface area. So meters cubed per day is the flow rate. Meters squared is the surface area. It's Q over A sub S. Again, that's our overflow rate. So in order to find the percent removal, we're looking at this line that's shown in red here. So what we have is we start at the bottom. So this is our 50% line. So percent removal equals 50 plus, we'll take the difference between these two ISO concentration lines and that midpoint right there. So it's plus 2.0 is the depth. We will always divide by the assumed height times 60 minus 50 plus 1.3 over 2.5 times 65 minus 60 plus 0.9 over 2.5 times 70 minus 65. I'll go back to the diagram in a second. Plus 0.4 over 2.5 times 100 minus 70. And that equals 67%. So what we calculated here, was that at a detention time of 70 minutes, an overflow rate of 51.4 meters per day, we would get 67% removal. So we're just looking at these distances. You can see here. And we always assume this top line is 100%. So basically at zero depth, we have complete removal. We will then do the same for a second overflow rate and detention time. So we'll take this 40 here. And drawing these are not trivial. This is an approximation. But if we look at this line here, it crosses at about 46 minutes. So we have an overflow rate here of 2.5 meters divided by 46 minutes times 1,440 minutes per day. And that is equal to 78 meters per day. So the percent removal here is equal to 40% because we're using the 40% line, plus, well, same procedure, take that midpoint divided by the depth times 50 minus 40, the difference between the two iso concentration lines, plus 1.1 over 2.5 times 60 minus 50 plus 0.75 divided by 2.5. And what you choose as your iso concentration lines is really arbitrary. It's based on the data that you have. And the more, obviously, the more iso concentration lines, the greater sort of the accuracy. But again, this method is really experimental, and I wouldn't have more than about 5 or 6 at my iso concentration lines. And this gives 57%. Okay, so what that says, if we go back here, at a 46-minute detention time, we would get about 47% removal, and at 70 minutes, we achieved 67%. And the goal was 60% removal. That's typical removal one would achieve in a primary sedimentation basin in a wastewater treatment plant. Okay. And so the question is, how do we know what red line to choose? It really doesn't matter. What you'll see in a second, what I'm going to do with this data in order to estimate that 60%. Basically, you're going to interpolate. So you need to pick detention times that bracket the removal. So for instance, if I had picked a red line down here, you would have seen I would have had, let's say, maybe 41%. And this is just a guess. Okay. I haven't bracketed that 60%, so I need to pick a third line. Okay, so once I've done this, I'm now going to plot detention time versus percent removal. Because remember I said I'm bracketing this value? If I bracket the removal, I've plotted, this is my 2 data points. So I've got a detention time of 70 minutes, and I've got a detention time of 46 minutes. And at 46 minutes, I achieved 57% removal, 67 at 70 minutes. What I want is 60% removal. So that occurs at a detention time of about 53.5. I do the same thing for the overflow rate. So for the overflow rate, I have here at an overflow rate of 51.4, I have 67%, and at an overflow rate of 78, I have 57% removal. Draw a straight line, do the same thing. I have 60% here, and that corresponds to an overflow rate of 70 meters per day. Now, we're going to add or multiply by scallop factors. Remember, what we have here is a column, and we're sampling. We talked about horizontal settling basins as having 4 zones. So what were those 4 zones? One is the sedimentation zone: inlet, outlet, and sludge. And if you remember, we have the potential for turbulent flow in these regions of turbulence to occur because of, in the inlet zone, we've got flow in the outlet zone, we have flow over the weirs, and in the sludge zone, we have, and I'll show you later in just a bit, the scraping mechanism. So that can create turbulence. So because of that, what we need to do is we need to use scallop factors to adjust for the fact that our basin has to be much larger than what we would predict based on this analysis. So based on that, our detention time will take this 53.5 minutes, and typically we multiply that by a factor of about 1.75. So we're increasing it by about 75%, and that would give us a detention time of 94 minutes, or about an hour and a half. And that is typical. Sedimentation basins, anywhere from an hour and a half detention up to 4 hours of detention. So the water is residing in that basin for a significant amount of time. And our overflow rate, we will decrease. So we'll take that 70 minutes per day. We will multiply by 0.65. It's a larger surface area. Our flow can't change. The only thing that can change is the area. So the surface area has to increase, and that would achieve a overflow rate of about 46 minutes per day, meters per day. So that's how we typically design type 2 sedimentation. Any questions?
Yeah, where did the 0.65 come from?
So these are just, they're rules of thumb, simply based on experience. So based on experience, we know that we should increase our detention time by about 75%, and we should decrease our overflow rate by about, multiply by 0.65. And you'll see that throughout, and in much of water and wastewater treatment design, you'll see these rules of thumb. Many of the recommendations that are provided in the textbook are really rules of thumb. They're years of experience, hundreds, thousands of these units that have been designed. And based on that, the industry comes together and says, okay, these are the ranges, for instance, you should use for detention times. If you use, for instance, in a secondary clarifier, actually in a primary clarifier too, in wastewater treatment, if your detention time is too long, then you've got the sludge that sits in the bottom, but that sludge is organic. And then if it starts degrading and producing carbon dioxide and methane, you produce bubbles. You kind of think about it. Here's my particles that I'm trying to settle. So now I produce bubbles from the sludge. These bubbles are going to rise. My particles are settling. What happens? So what I have is a situation where I have wastewater treatment. My detention time is too long, so that I start getting biological degradation of the organic matter in the sludge. That produces CO2 bubbles, and it can also produce methane bubbles depending on how anoxic. What happens to my particles?
Could they get trapped in the bubbles?
Exactly, they get trapped by the bubbles, and what do the bubbles want to do?
They want to go up?
They want to go up, but you're trying to settle the particles at the bottom. So what do you think happens to your sedimentation efficiency?
Goes way down.
Exactly. Okay, so because of that, we know essentially, okay, if the detention time is longer than about 3 hours, we start to see decay. Or if we don't remove sludge on a regular enough basis from that bottom, then we're going to start getting significant biological activity, and you're going to produce these bubbles, and that's just going to do the opposite. Now, there is a process called flotation. where we actually design the system to do this, but sedimentation basins are not designed in this way.
So for the flotation, would you just scrape it off the top then?
Exactly. So flotation system, you actually add air to the system under pressure, and then you release the pressure, kind of like when you release the pressure, it's kind of like opening up a pop can. Okay, the bubbles all rise to the top. So with flotation, it's the exact opposite of sedimentation. You're actually using the bubbles to bring those particles to the surface, and you scrape it off the surface rather than scraping it off at the bottom like you do with sedimentation. Almost think of it as phenomenal. It's the opposite, whether you scrape it off the bottom or scrape it off the top. Flotation is used, I don't know if they still do it. East Lansing wastewater treatment plant used flotation to thicken the sludge from the secondary clarifier. So I drew the diagram the other day where you had a primary clarifier and then your biological treatment. You have then a secondary clarifier there, and they take that and the primary sludge and they use flotation to thicken it. And that's because much of that material is organic and it has a low density, and it's actually easier to float it to the surface than it is to get it to settle. So they can actually get better thickening with flotation. On the other hand, at the Lansing dye water treatment plant, they use gravity thickening because the softening sludge is dense and it's easy to get it to settle. So whether you use flotation or sedimentation, it really depends on the density of your solid particles.